So hello again. Tonight we're going to basically provide some basic education, a primer, you might say, on electromagnetic radiation. I talk about photons and electromagnetic radiation like everybody knows what I'm talking about, but people don't. And so I'll put this out there as reference material. People can look it up. It's not a degree in, particle physics or anything to that level because it's going to take less than an hour to go through it. So consider it as maybe some of the information might get past you, but there's lots of links at the back and you can always stop, back up the video once I get it published publicly. So as I said, I would like to engage with a wider audience. The first thing is the globe of the Earth is actually a Unicode font character. I did not know they had characters like that, but I didn't have to go grab a particular picture of the Earth and worry about copyright infringement thing. It's a character in the character set that is internationally agreed to be freely accessible. So Earth as a Unicode character. Fascinating. So, I've often said nobody's born knowing this stuff and they keep changing and adding new stuff all the time. But I've kind of had to keep up with it because computer hardware and software is my career background. So, I go back all the way to like IBM 360s and Kim 1 PC boards as little playable personal computers. And if you went through my storage of antique computers, I do have a VIC-20, Commodore 64, multiple Amigas, a number of Windows machines, desktops, laptops, and tablets. I actually own a card that went into my Amiga 2000 that had genuine Apple ROMs in it that allowed me to run up a Macintosh environment on my Amiga 2000, which was fascinating. I've owned Windows CE computers and like planners and things like that, as well as Windows mobile devices, a couple of Android mobile devices, and I played a lot recently with Raspberry Pi computers running various Linux packages. So it's what I know, and I know not everybody knows this stuff, and they keep changing it. So just realize that if I say something and it's not common knowledge, that I'm not doing it to deliberately drive it over your head, ask. Just say, what did you mean when you said multiprocessor? Or, things like that. Just stop and ask. And I've always thought that anybody that puts their mind to it should be able to learn what they don't know. As I jokingly said, so long as it's neither rocket science nor brain surgery, although I have discussed rocket science on occasion, and I have watched a lot of YouTube videos of neurophysiology. And did you know that one of the actors on Big Bang Theory was actually a neurophysiologist, PhD? So, and I've also worked on a medical standards project to do device integration of a sedation monitor. This is the thing that they use in the operating room that once the anesthesia knocks you out, they want to make sure you're actually knocked out and not just like in light sleep where you'll remember all the pain, but can't say anything or move to do anything about it. But you'll experience all the pain and memorize it. So they found that if you monitor the brainwaves, certain brainwaves, that as long as they stay within a certain level, a certain frequency and amplitude, that you are indeed unconscious and not aware of what's going on around you. But if it ever rises up, then you need to apply more sedation to bring it back down. And that's what the anesthesiologists do nowadays is they have a Stryker or other branded sedation monitor that they hook you up to in the operating room to make sure that you're really knocked out. So, I'm neither a rocket science expert nor a brain surgeon, and I don't see anything that I talk about as being above a person's pay grade if they're willing to go follow a few links, dive into some of those rabbit holes that I create. So I've talked a lot about photons and the electromagnetic spectrum, like people knew what I was talking about. I've also realized that, you'll never know how much you didn't know until you know what you didn't know. And that's not only my audience, but myself as well. So to that end, this presentation may sound a bit straightforward to some of us, but remember, I'm going to post-process it and publicly publish it out on YouTube for other people to learn a thing or two about a thing or two. So photons. A photon is known as a boson. This is one of those numerous particles in the world of particle physics. The class of it is a boson. It is specifically the carrier, which bosons are carriers, of electromagnetic radiation. So if you want to package up energy and exchange it between atoms, photons are how you do this. Now, a photon is not inside of an atom, so to speak, like protons, neutrons, and electrons, and they don't form matter itself like fermions. So there's lots of different particle names for all these different particles, and it's a big particle soup out there. There are standard model pictures if you really want to get into it. Just Google standard model of particle physics. And I'm not going to delve into the particle wave duality of photons. Just suffice it to say that a photon, when it's at rest, if it's ever at rest, is massless, doesn't have any mass. And when it's moving about, it can transfer its energy as momentum to other things. And that the level of energy it has is expressed as a wave, as an oscillation or frequency wave. And there are waves, photons, that are less than visible, like radio waves and infrared. We can't see with our eyes, but like infrared is used at your TV remote control, where your TV can see it. And if you actually push the buttons on your infrared remote and you hold your contemporary Apple or any generation Android camera to it and do a live view, you can actually see what looks like a little purplish light coming out of the infrared remote control. And then if you point it at your face, you can't see anything. So the camera is more sensitive to infrared than is your eyes. And then there's the visible range. All those pretty colors, that's the visible range. And then higher energy takes you above that into ranges where, once again, the human eye cannot see. This would include ultraviolet, X-ray, and gamma. And X-ray's been used in X-rays, so to speak, and gamma is used in gamma knife surgery for cancer patients and such. That wave, the electromagnetic wave, has a propagation orientation. If you see that wave curve there on the slide, if you were to take that and think of it as flat and going up and down, if you were rotating that out towards you, that would be what we're talking about. We're talking about the orientation of the wave. The wave stays the same. It's just which angle is coming in your direction. That's the angular orientation phase of propagation. And if you want to see this, the easiest way is get yourself an old or cheap pair of Polaroid glasses or polarized lens sunglasses. Take the two lenses out, hold up one lens, hold up the other lens on top of it, and then look at something in the daylight, and then rotate the outer lens 90 degrees, and everything goes black. That's because the polarizing lens is nothing more than a wave front, and the wave front has gaps in it. And one of the lenses gaps are oriented this way, and the other lenses gaps are oriented this way. So it allows the light to only pass through if the wave is sideways as opposed to up and down, because there's not enough space between the refringement gaps to allow the other phases of light to come through. This is not color blocking. This is not brightness blocking. This is phase blocking. And the reason why things look darker when you block out things that are out of phase is because you've literally dimmed the brightness that's getting into your eyes down, because our eyes can pick up multiple different phase orientations. So you've reduced the amount of brightness coming in. That's why things look darker. And they look sharper because you no longer have two different phases interacting with each other within your retina, where your brain has to figure it out. It's just one. But the phase is not necessarily at 0 and 90 degrees. It can be at any orientation. Oh, as to the symbology here, the lambda, Greek symbol lambda, is the symbol for photon, wavelength, frequency, energy. That's how you represent the frequency or wavelength of a photon is with lambda. Photons are on a spectrum. Remember me saying it's a wave? See that red wiggly thing there, how it gets long as you go from radio, and then you get shorter and shorter at higher frequency as you move towards infrared to visible to ultraviolet, X-ray to gamma. The peaks get shorter. The distance between the wave peaks and troughs gets smaller. So you have a collapsing wave. As the color changes, different waves. And then if you wanted to measure things, the scale, there's a horizontal scale that we see to humans in the buildings, the scale of the waves, we look at the visible right there in the middle, and the wavelength of the actual photons are on the order of 10 to the minus 6. That says half times 10 to the minus 6. You know, minus 9 is a nanometer, so minus 6 is more like a micrometer, which are the size of bacteria. So as you go towards the infrared, microwave, and radio, the waves get much larger, and low frequency radio waves can be very long indeed. And then as you get towards the higher end, one of the ways that allows ultraviolet C band to destroy viruses and bacteria is because the wavelength is energetic and so small that it fits inside the cells that make up the bacteria or the virus, and it actually breaks the DNA up. And when it does that, it either mutates or it will destroy the cell. So that's why they use UVC to sterilize things. And they also use cobalt radiation, which is, you know, beta radiation and such, as means of destroying things, bacteria and viruses and food that gets shipped. And then the gamma knife for destroying tissue. You can also measure not just the wavelength, but the frequency, how many cycles per second the wave is oscillating on. And you can see the color versus the wave frequency. And then another thing that I knew but didn't pay much attention to is you can measure the energy of a photon by its temperature. Temperature as in energy as in Kelvin, just another way of measuring how much energy does that photon have. So as of tonight, we're going to start using some of the materials from the NASA JPL Night Sky Network program, which is actually executed by the Astronomical Society of the Pacific. They create educational presentations and banners that are openly accessible. Schools, you know, love that kind of content because it's ready-made. And if you're a Night Sky Network member, like Broward Astronomy is, then you basically produce presentations, give it to your audience, and then you record that on the Night Sky Network website. And when you do 3 or 5 or something like that, then they will send you future kits, which only Night Sky Network members that do convey the education out to the public are allowed to get. They produce educational content for adults and children about science, technology, engineering, and math, space exploration, and the universe. One group of their presentations is called Big Astronomy, and within there they have something that is a presentation called Clues to the Cosmos Activity. And it does talk about the various colors of things and how you can use filters to selectively look at things. So if you look up at the top, you'll see a color wheel that has colors. You don't see white because white is a mixture of colors. You see black all around the outside. That's an absence of color, at least as far as additive color goes. And then you see this jumble of letters, and they actually have a message in there, but because all the different colors are showing up, you can't quite read the message. But if you use a red filter, so only the red stuff gets through, then you can actually read it, and it says that the letters spaced out. Now you see the light. So what they did was they created an app you can use on your phone to create color filters that if you hold it up to the color wheel, you can actually see on the phone, which parts based upon which color filter you're using. And another one of the Night Sky Network presentations is in the grouping called Telescopes, Eyes on the Universe. And the material content is the universe in a different light. I have a link at the end if you want to go look at the details. But in there, they have pictures of various astronomical objects, galaxies, and such, and they will show them to you at different wavelengths. For example, they had Jupiter at various wavelengths, including radio. But the one that I thought was most striking was Saturn. And you can see the typical yellowish looking Saturn there in visible light on the lower left. And then in infrared, obviously infrared, different colors of red that are a wavelength longer than human vision can see, but the sensors can pick it up and translate that into computer data, which then gets mapped into visual colors. So you can see the darker bands and the lighter bands of the rings and the planetary weather pattern. And then if you want the higher energy, you can look at Saturn in ultraviolet light. I'm sorry, the scale is a little different, but you can see the north and south poles of Saturn have a lot of ultraviolet coming out of them. That's why they look brighter. So whenever I say electromagnetic radiation, people hear the word radiation and their ears perk up. They're like, radiation, isn't that harmful? An emission of photons is electromagnetic radiation, but not all of it is high enough energy level or high enough flux to cause any physiologic damage. In high intensity microwaves, UV, X-ray, or gamma, those are things to be concerned about. But strangely enough, they also call radiation, not electromagnetic radiation, but particle radiation, the emission of cores of atoms, alpha particles, cosmic rays, or atomic radioactive decay, beta particles, because these are large enough, moving fast enough, and are energetic in that they can fragment DNA in cells and either mutate cells or destroy them. So all photon emissions are considered electromagnetic radiation. If they're low enough, we don't see them. If they're low enough, they're not ionizing. They don't ionize. They just excite atoms into producing photons that, we can see visible light. But then there's the parts that we don't see, like radio, infrared, and ultraviolet. When the energy levels are high enough in the photons that they can actually not just get a photon released from an atom, but they'll actually strip electrons from atoms. That's called ionizing radiation, as in the ions are the electrons that get excited to the point where they actually leave the atom. Ionizing radiation at sufficiently high levels are a concern because they can damage your DNA and destroy cells. But use of the word radiation has context. So is it ionizing? Is it not ionizing? Is it a harmful enough level? Is it not? What was the duration of exposure? What was the level of exposure? What was the flux of it? And how often did you do it? You can get a dental x-ray once or twice a year. You can get even a chest x-ray once or twice a year, but you don't want to do it every day. Even if it's the same level of x-ray radiation, just the fact that you're getting exposed to so much of it can be damaging. So short duration, non-frequently repeated exposures of low fluxes of even high energy photons are tolerable, or x-rays, CT scans, PET scans, things like that. So how do we measure our observations of photons? Well, we measure them obviously by the energy and the energy frequency and the wavelength, but we measure the wavelength in scaled meters, or color if it's visible light, or we can also measure the energy and temperature of Kelvin, but we typically measure the energy as the color of light. Is it red? Is it yellow, green, blue, purple, violet? Orientation, we don't get into that too often in light. We do in radio. An antenna can pick up a signal that's coming in a certain orientation, and if you don't do something about it, if you're receiving a radio signal that's 90 degrees to that orientation, you'll not receive much of that signal. But if you have a two-lobe antenna that can pick up 0 degrees and 90 degrees orientation of the phase, you're going to get a stronger signal level. And then you merge the two of them together. So the amount of photons, the density of them, flux density, as the saying goes, although not flux capacitance, that's something different, or the radiance or the quantity of photons per second over a square area, whether or not you're considering how far away are from it, and whether or not the particular brightness or emission is biased by human retina physiology to, say, 555 nanometers is the bright peak versus just scientific measurement of brightness. You can actually have a deep blue light that is actually far more photons per second than a green light with fewer photons, and your eye will think the green light's brighter because human vision is more receptive to green light than deep blue light. So it may look dark blue, but it actually is producing more photons and more energy, more brightness is coming into your eyes than you can physiologically detect. So the amount of flux, the energy level, we refer to it as radiative flux. This is the number of photons transferred over a square area. And that takes into account the distance from the source. So when you're talking about how far away a star is and how many photons you actually detected, you can take that radiative flux and include distance as how much you would expect. You'll often hear air conditioning and heating units measured in British thermal units or BTU. That's heat flux. That's the rate of heat flow across a unit area. Then you have one of my favorites, momentum flux. This is the rate of transfer of momentum across a unit area. How many newtons of force are the photons transferring to a material, including, I don't know, a reflective mirror at the LIGO Gravitational Wave Observatory. And then the one that you may not be aware of it, but when you go to the store and you want to buy a light bulb that's an LED, what's the efficiency of it? How many watts do I have to put into the light bulb to get how many watts of particle flux out of it? So if you say, I'm going to go buy myself an 8-watt light bulb, you buy yourself an 8-watt light bulb, and then you find out it consumes 8 watts. What is the wattage of the photon flux coming out of it? It's about 7 watts. Where'd my other 1 watt go? You ever see that bulb get hot? The electronics in it heat up? It's taking 1 of your watts and converting it to infrared heat in the electronics. Usually it's the AC to DC converter that gets hot. The actual LED doesn't get that hot, although you can get really hot LEDs because a small percentage of inefficiency with a very high wattage, like if you had a 50 or 100 watt LED, single emitter LED, even if it only had 12% inefficiency, that's still a lot of watts of infrared. So they can get hot and need heat sinks and fans and cooling. So how do we actually measure it? How do we measure photons? It's something called the photoelectric effect. It's that guy Einstein again. When a photon encounters a sensor material that has appropriate metallic properties, the photons will be converted into an electrical charge. It will basically excite electrons. And the electrons that get excited and produced will flow with a known voltage level. Photon, electron, conductor, store, and different colors, different wavelengths. You need different sensor materials in order to convert that particular photon's energy into an electrical value, a voltage. But the odd one is if you want to measure infrared, you use things called bolometers or bolometers. They take a known voltage, they pass it through a little sensing material, and if light in the infrared range strikes that sensing material, that bolometer infrared pixel, it will change the resistance. So you're not measuring the voltage coming out, you're measuring the change in voltage, and that says how much infrared's actually being received. But in radio, in older radio, non-digital radio, back in the days of analog radio, you would use tuned coils. You would have coils of wire that the electromagnetic radiation from the radio signal would oscillate in. And then you would use an air gap capacitor that had multiple plates in it to tune the frequency that you want, because it would lengthen and shorten the circuit path. And that would fit the particular wavelength, because remember, radio waves are long. It would fit the wavelength, and that's the signal you would tune. But nowadays, it's all done digitally with phase lock loops and such. So using coils and air gap capacitors is a stylish old thing to do, but I don't do it anymore. I use digital ones. So as the photons make it into the sensor material, you have a duration or exposure that shall allow the photons to be converted into electrons to produce a charge. And you're going to gate that charge. You're going to hold it back and let it build up like a water level. Let it build up. In the case of CMOS cameras, that's a capacitance. In the case of CCD cameras, that's a charge that you'll have a transistor that can be turned on or off to either hold or release the electron flow. In the case of an old analog radio, it went straight out and would go into the coils of a speaker. So the electromagnetic radiation would actually vibrate a speaker. And if you were listening to AM radio, it was very straightforward to get the radio signal to vibrate the speaker, and therefore you could hear it. But nowadays with FM and all sorts of other, satellite radio and satellite TV and such, you need solid state radio receivers to pick all that stuff up and to demodulate the signal. But once the signal gets converted to an electrical level, a voltage, it then will be passed through a low noise amplifier to boost the signal up to the point where it's detectable. And then that voltage will go through an analog to digital converter to actually convert the analog voltage into a numeric value. So you can see the string of letters down at the bottom. Photon, lambda, becomes electron, becomes voltage, becomes number, or goes directly to speaker. So if you want to think of how do we measure photons, how do we measure the wavelength, the energy, it's photons become electrons, become voltage, voltage gets converted to a number, and therefore you have the number. And then if you measure that over time, you can determine the frequency of it. So to wrap it all up, photons are bosons, carriers of electromagnetic radiation. The range of photon wavelengths is the electromagnetic spectrum. They can be lower energy and just exciting atoms to produce photons, or they can be higher energy and actually ionize off electrons. Not all electromagnetic radiation emissions are immediately harmful. There's low energy, high energy, there's exciting or ionizing. The harm context has to do with things like nuclear decay, the level of energy, how much of the energy is there, how long you were exposed to it, how often you were exposed to it. Electromagnetic radiation, just as a concept, is not directly harmful. Historically, we've measured the photoelectric effect to determine the wavelength of a specific sensor. We need different materials for different wavelengths. But as I mentioned a couple of weeks ago, now there are people working on sensors that do not use the photoelectric effect. They actually use the momentum transfer of the photons to measure their color directly, which I think is fascinating. It's like going from smoke signals to radio. It's conceptually, you're still communicating. It's just a completely different technique that would not have been available to you until you advance the technology to a certain level. And in the case of cameras, you put filters over the individual pixels called a Bayer matrix to allow you to pick up multiple different frequency ranges with the same sensor material. And therefore you can pick out different colors. So this is just a brief primer on electromagnetic radiation. I'll soon show you a couple of slides where there's links for those who are seeking deeper rabbit holes. Plus, there's all kinds of YouTube videos out there. So, a bunch of Wikipedia articles, just giving you the basics. And then the two Night Sky Network reference materials. Okay, comments, question. Did it miss anything in your understanding of photons? Did it create questions that you need answers to?
I have to absorb a little more before
That's
I
fine.
come to my questions.
That's fine. And I'm always available, like in the coming weeks.
Yes,
I don't narrow it down and say, you can only ask about this week's presentation this week. You can say, like 2 weeks ago, you were talking about this.
exactly.
That's
That might
fine.
happen.
That's fine. That's not a problem. Not a problem. And yes, a lot of it requires additional reading material,
Exactly.
watching
Really.
things. So, or as I was saying yesterday, there was one of the people at the Fern Forest Nature Center event who said, "You're not one of those believers in the flat Earth theory, are you?" I said, "I've got a telescope and a mobile phone." No. What do you mean? I said, "Well, the Earth is flat if you measure a few feet around you. It looks flat, it feels flat. But if you go out for miles in any direction, the land actually drops away and there's curvature." I said, "Do you own a mobile phone?" Yes. I said, "Have you ever used the mapping in the mobile phone? Like, go find me the nearest gas station or restaurant." "Oh, I use it all the time." "Did you know that it makes use of GPS satellites that orbit the Earth? And without those, you wouldn't be able to tell where you're at?" He just went quiet and I just walked away.
Well, what made him think you were a flat Earth person?
I don't know. I
Exactly.
he
That's
couldn't
it's
see me in the dark. He just knew I was a tall, older guy, had a deep voice. That was all he could tell. I was actually wearing a black T-shirt that had small white lettering on it that says, "I void warranties." I don't know that he could read it in the dark, but that was something Helen gave me years ago.
that's
You did,
amazing.
yeah.
I
You
love
you
it.
did say something tonight that I didn't hear before, or it surprised me, and it
Mhm.
makes me think. You said, and I don't know if I heard it correctly. You said something about the photon is not part of the atom.
No,
Doesn't have to be part of the atom.
no. You have protons, neutrons, and electrons. Those are what make up an atom. And then the neutrons and the protons actually have quarks and gluons inside of them. That's what makes up them. But
Right.
the photon, you can't decompose any further, as far as we know today. You can't decompose it any further. And photons do not hang out inside of atoms. A photon can excite an atom to make an electron move to a different orbital. And then the electron wants to get rid of that excess energy and it will produce a photon, and the photon will leave the atom. But photons don't normally hang out inside of atoms, they're not part of atoms.
So not all atoms have photons.
No atoms have photons.
Okay. So molecules have photons?
Molecules? No, molecules are collections of atoms.
Atoms, right.
Yes.
Photons are with other elementary particles like protons, neutrons, and electrons. You have conservation laws. So if you get rid of a neutron in something, you can have a proton or something, and when one disappears, you get another, and they're conserved. With
Yes. Yes.
photons, it's not the case. They aren't there. They can be created one or 1,000 of them out of nothing, and then when they're created, so when you have an electron, say in an outer shell, and it jumps to an inner shell, it's going to have less energy. So it gets rid of that energy in the form of emitting photons, and they come out of nothing. It's just the way that the energy is emitted
Oh.
when it goes. Then when those photons reach an electron somewhere else, the electron will jump to another shell and an outer shell, and the photons disappear. Isn't that right, Monroe? I think that's right. There's no conservation of
Yep.
photons.
Yep. A
And isn't
photon.
that sort of interesting about the nothing theory of like when we were thinking about um, Monroe was giving the presentation and he was saying that we used to say that the speed of light was, we thought that there was nothing could be over that, and then it goes to nothing. You go from here to there instantly, but that's not really what happens.
No.
And I'm thinking that maybe we have to discover something to see what this nothing is. Maybe we
Yeah.
don't have the wavelength ability to see that yet. maybe there are other wavelengths that we don't see or don't know of. There are wavelengths we don't see.
Not necessarily wavelengths, but interactions, particle interactions. So it was always considered that when an electron gets energized, it moves to an outer shell layer instantaneously. There's just nothing that happens in the meantime. It's just there and then it's there.
Yeah.
And now that we have attosecond quantum interference that we can measure, things down to the attosecond level, we can actually see that the photon comes in, the electron gets excited, and then accelerates up to a speed which is less than the speed of light, and then it stops at a shell, and then it goes, wait a minute, there's too much in this shell, and then it emits the photon, and then the electron accelerates inward towards a more stable level within the atom. And they found that the speed of acceleration, the acceleration level going in to out, is faster than the acceleration level going out to in. But it's only because we could now measure things at a much higher level, smaller time. And it was also thought at one time that photons are unable to interact with one another. Photons are always just like ships passing in the night. They never interact with, you can't slam two photons into one another, until we found out that, if you can align atoms and you can energize them with sufficient energy that they emit their photons at the correct phase angle such that the photons are directly head on into one another, you can actually get a photon to smash directly into another photon, annihilating both photons. They actually get antiparticles and other wavelength photons to come out of it. And the weird thing is the sums don't match. In other words, if they say, we finally got two photons of this wavelength to smash into one another, and we detected all of the particles that came off of that, and the sum of all those energy levels of those normal state and antimatter state particles, they don't all add up to the collective head-on energy collision force of the two photons. So there are things that go bump in the night that we have no ability to measure as of right now. Our science just can't. It's like I did the presentation regarding photons that we can't currently measure because we don't have the material science for doing so. Once a radio frequency gets low enough to the point where it's a fraction of a cycle per second, we have no photoelectric effect technology, no semiconductors, no materials that can measure energy levels that low. But we know the photons don't just disappear. We just can't measure them. And if all photons start out at a higher energy level and get clipped and eventually get lesser, they get redshifted. Take redshift further. It goes from, let's say, gamma to X-ray to UV, and then it gets into visible, and now it gets into red, and then it becomes infrared, and then it gets down into radio. We know all that stuff happens. What happens when it gets really, really low frequency radio? Like, down in the extremely low frequency range under 60 hertz, we can still read that. We've still got radio receivers that can detect that. What happens when it gets to be less than 1 cycle per second? Well, we know the progression of photons can get down that low. It just gets to a cliff edge where we just don't have any sensing technology that can detect them anymore. So how many of them are down there? Don't know. But they're down there. But they don't interact. They might be this thing that we call weakly interacting particles, or WIMPs. But things don't just disappear. As Adam was saying, there's conservation of momentum, conservation of energy. These conservation formulas, which are not inviolate, there are physical principles where things aren't perfectly conserved. And at one time, we thought that was the case with nuclear fusion. we would measure the particles associated with the fusion in a star or a supernova, and we go, wait a minute, we're missing something here. The sums don't add up. And then we postulated these things called neutrinos. And neutrinos were that leftover gap. So you can think of neutrinos as the leftovers from stellar explosions or fusion. And then we found out, oh, there's different energy levels for the neutrinos, and they can shift energy levels as they go propagating through space. So somehow they're interacting with something that causes them to shift their energy levels. And so you have different flavors of neutrinos. So keep studying, keep learning more, keep creating new technology, new math, new science, and then layer it one on top of another, connect the dots. And maybe you'll find out that instantaneous is just something we use until we figure out how it actually works. Dark, like dark matter, dark energy, is just what we say until we know what it actually is. And that small levels of stuff over immense quantities actually produces very large effects, which might be how the stars at the outer edge of galaxies move at equal velocity to the stars towards the center of the galaxy.
So in my science knowledge or basics, I think of just in high school, like the atom and the molecules, and then later on you find out about neutrinos and all this, but that wasn't while I was in school. But they still broke it down, so everything was happening inside of the atom, that it built up when you went to another level, and that it was all encased in this atom and then molecules and then, cells or whatever. But it's showing that it kept breaking down, but this photon is not encased in that. That's an interesting, how do they show that as breaking? They don't show it breaking down, that I guess.
No.
There's no levels that they go through?
No, and in fact, they claim that photons are not decomposable into new types of particles, because when they finally got photons to smash into one another, all the particles that came out were ones that we already knew, like, positrons, which are positively charged electrons, gluons and things like that, and anti-versions of that. Those are all things we knew. So by smashing photons into one another, we got no new particles out of it. But how many years do we think photons are completely indivisible and there's no way to break them apart? Well, we just had to have science and technology advance a bit. And yeah, there's a way you can get it to happen, but we didn't find any new particles as a result of it. But where we got atoms from is before we could even detect atoms. Atomos, ancient Greece. There were people believing that everything is made up of the same things, and those things are just too small to actually see, but everything is made up of the same things. So even before they understood protons, neutrons, and electrons, they postulated that all the material, everything, is made up of these things called atoms. And until we started...
But photons isn't made up of atoms then. It isn't made up of, or even broke down inside the atom.
As I was saying, the more you know, the more you find out that what you previously knew wasn't quite right. It's kind of like the difference. It's kind of like the difference between Newtonian gravity and Einsteinian gravity. They're both gravity. They both produce the same effect. If you drop an apple, it still falls to the ground. But for smaller, slower speed things, Newtonian works just fine. But the moment that you get on very, very small scales or very, very high speeds, Newtonian, the numbers don't come out right. But as soon as you apply relativity to that, in fact, special relativity, it all works once again. Well, the same thing holds true. We can decompose atoms into protons, neutrons, and electrons, but that doesn't mean atoms don't exist. It just means we've picked them apart and found some new stuff on the inside. If you never opened up an apple, you would never know there's apple seeds on the inside. But the moment that you eat the apple and you get into the core, or you slice the apple in half, there's seeds in there. Well, the same thing can be said of particle physics. If we get more and more energy to smash things harder and harder, we can break apart that apple and see what's on the inside of it.
But up until tonight,
Mhm.
if somebody came to, and said, "Oh, Joanne, you know a lot about this stuff or something,"
Mhm.
and I'd say, "Oh, yeah," I would always have thought that could have been a breakdown. I thought that photon, that's what I was missing. I go,
Mhm.
why don't I understand about this? It's because everything breaks down under the umbrella of molecules break down into atoms, and atoms break down into this, and each one of those break into this. And I thought everything, like the Greeks said, everything was of this one thing. Everything was made up of this. But if this is outside of that realm,
Mhm.
that's sort of like, oh my gosh, it's hard to think of.
Do a Google search for standard model particle physics. And what you'll find is all the substantive particles that we know about below the layer of an atom, those are all fermions,
Yes, I understand them.
matter particles. But there's a whole other category of those that are for carrying things between atoms. Like I want to carry energy from this atom, excited electron, to this other electron in this other atom over here. I want to carry that. Those are carriers. Those are called bosons.
Those make sense to me, but this doesn't. This photon, the thing that comes outside of the traditional model is just amazing.
But they aren't the traditional model. They're just like the model we knew when I was growing up. Like I knew that there were subatomic particles out there that were below atoms. I knew about protons, neutrons, and electrons. But when I was in middle school, we didn't study quarks and gluons.
Oh, neither did I.
Right.
No.
So, as I said towards the beginning of the presentation, they keep adding stuff. They keep changing stuff. What you thought you knew, well, that kind of still exists, but now we've got a finer understanding of it, and it's not quite exactly as opaque as we thought. It has texture to it, it has detail to it.
This being outside of the atom,
Yeah.
and not being making up of an atom is like really out there. I can get the fermions and the quarks and the charms and all that stuff because it all still breaks down and it's still inside the atom that everything is made out of.
Yep.
And so, but this is something new to find out something that's not inside of that breakdown. Is not part of everything is made up of this.
Well, it's photons are not the only thing that's out there outside the atom.
Okay.
Anything that's a boson, that's a carrier, there is the mass carrier, which
But
is
you're saying this carrier is still part of the atom. It was
No,
part of
no.
one atom and it traveled to another atom. It was
yes,
part of
It's
one
not- it's
part of
not-
one atom to another. But it originated and it's part of when you break down the atom.
but it's not part of the atom. It's emitted by the atom, but it's not part of it. It comes out of
But
the
then
atom.
the photon isn't even part of isn't even
No.
transmitted by the atom, right?
It originates from an electron within an atom, but
Ah.
it's not a part of the atom itself. It's not a proton, neutron, or electron. It's a carrier.
But you could not have a photon unless you had an atom. Is that true?
Not quite. There are things called scattering, where you can have a field of electrons in free space, like electrons outside of atoms that have been ionized from atoms, and they're moving in free space, and they encounter photons, and those photons can energize the electrons. There's no shell, but the photon energizes the electron, and the electron now has too much energy, and it will spit out a photon. This is things like Compton scattering. That's named after a guy named Compton, obviously. But Compton scattering is when you have a field of electrons outside of an atom and it encounters electromagnetic energy in the form of photons, and those electrons get energized and produce photons. So Compton scattering. There's another one called Rayleigh scattering. It's slightly different, but it's scattering. And scattering is one of those things that need not obey the laws of conservation, at least the conservation of energy, which if you talk to certain classical physics people, that's an anathema. Like, well, you know that Compton scattering is one of the things that happens in X-ray tubes, and there's millions of X-ray machines around, and they seem to work just fine. You know, we're not missing any energy anywhere. So yeah, whenever somebody says that's the way it's got to work, like, okay, where did that originate from? How long have you been hanging on to this dogma? And have you been keeping up with the latest in physics? Because the more we crack things open, the more we learn. The faster we can decode things, the more we learn. Now, simply because you learn something, it need not necessarily change what you already knew. And it will probably not have a direct effect upon you until somebody produces a consumer device that makes use of the principle, like a MEMS-based microphone in your mobile phone. Standard particle physics, or standard model of particle physics. There's an entire collection of subatomic particles there, and they've got their antimatter and matter variants. And you've got fermions, and then you've got bosons, and then you've got the ones that clump up to groups of those called leptons. And, but you know what? In everyday life, it just doesn't matter, because it's just matter.
Right.
Matter just sitting there by itself does not self-destruct in a fraction of a second. Now, there's energetic chemical reactions. You know, you can drop lithium in water and watch it go. But, you know, if you mix salt and water, there's a chemical reaction going on. But it's not that energetic, but it functions. It does things. You get salt water.
Yeah.
So there are things that directly affect us, and they're pretty non-energetic. There are things that we do that we want to be energetic because we want the energy from them. We want the heat from them, like internal combustion engines, like cars and trucks and airplanes and trains. And, you know, those are explosive chemical reactions. And then we realize, you know, if we just take electrons and run them through coils and create magnetic fields, and the opposing magnetic fields will turn a rotor, now we can go down the road and we don't need any of the burning fuel. And if we actually use solar panels or wind turbines to generate the electricity that we consume in our car, they don't need to burn fuel either, not even natural gas. That's why I always think of it as my ground level, my how I need to remember to think of things to avoid getting stuck into a scientific form of dogma is we no longer communicate using smoke signals because they wouldn't work long range and they're just not efficient enough. We use radio. We're advanced people. We use radio. But someday in the hopefully not too distant future, when we learn to create gravity waves, we're going to find that gravity waves are far more efficient and far more effective at communicating very long distances than is radio. It's just going to be what happens. It just is.
I have to wait to find it.
Yeah. Now, we're detecting gravity waves. We're detecting a background field of gravity waves. When we can make a desktop gravity wave detector that will work at the appropriate wavelengths, we may find that I see modulation here. You remember in the movie Contact, when they were getting the radio signal from Sirius and they were listening to it on the headphones, and they said, I hear modulation here. And then they ran it through the computer radio receiver thing, and they could now see that, oh, this looks like it has structure. And then they found out it's an NTSC style 1940s video broadcast. And wait a minute, I think there's another channel here. Sounds like audio. And they decoded the audio, and now you had a moving picture and a soundtrack to go with it. Well, once we can actually demodulate gravity waves from the background gravity wave field, like the cosmic microwave background, once we can demodulate gravity waves, we may find they've been talking to us all along. We just didn't know how to listen. One person's opinion.
Monroe, you mentioned before the page, the Facebook page of Helen's about a video on microwave.
Microwave
I couldn't
oven, yep.
read. How does one get hold of it? How can I?
It's very simple.
Yeah.
Give me a second. I'm going to switch out of this sharing mode.
Because I couldn't read it. It was too fast.
That's okay. I will make it easier. And I might edit it out, but I'll still be recording at this point. So I'm going to go to Helen's Facebook page. Do you know how to open the chat window in Zoom? There should be a little button that says chat. Let me get down to it here. I know it's here. I remember seeing it. There it is. It's on Tom Scott's YouTube page. So if I now go to Tom Scott, now let me share. I will once again share screen 2. Okay.
Now, Tom Scott.
So this is Tom Scott's YouTube page.
Okay.
It's pretty interesting to watch. And I will scroll down. Well, actually, the easiest thing to do is when you get to a page, let's see, filters. I don't want filters. Search. You can search on a page. Looking for something in his site, I can just say microwave.
Okay.
And it should, bingo, take me to the video. And
Yeah.
I now,
Okay.
no, I'm going to make it really easy.
Click on share below the video.
Copy link, there it is. Now, if I go over to my Zoom and I open chat and then I paste that link. Okay. Do you see it in your chat window?
Yes.
Yes.
Yeah. Now, once it's in the chat window, if you right click on it, you can say copy link. And then you can go to your friendly web browser, open a blank page, and in the address bar at the top, right click, paste and go. That'll take you right to it.
Yeah, I can get it.
See? Whereas
I have a question.
as I like that old Star Trek adage, many journeys are possible with me as your guide. You have a question? Yes.
Yes. You had mentioned gravity waves
Yes.
and that we're going to find them in the future. My
No.
question,
We've already found and confirmed the existence of gravity waves. What we've got right now is confirming the existence of a gravity wave background. Like they're everywhere from lots of places. That's what we're confirming right now. And I'm saying
yes.
once we realize that there's a lot of gravity waves around us, we're going to want to tune in on them and see where they're coming from, and are they, stars colliding or supernovas going off, or neutron stars or black holes merging. And I think eventually we're going to find out it's the next thing past radio is gravity wave modulation. And once we find a way to create gravity waves and modulate them, which just means switching them on and off really fast, we're going to find out that there are gravity wave sources in the universe that have been sending us messages all along, but we just couldn't know what they were saying or how to receive them. So
Yes, and I understood that.
Yep.
What I wanted to make sure that I wasn't making, I'm making an assumption that I don't know if it's correct or not. And my
Okay.
assumption is that gravity waves are related to gravity. And am I correct?
the physical expansion and contraction of space-time alters gravity. And the gravity waves is kind of misnomer.
Okay.
Space expands and contracts, and the way that we detect that is as if gravity increased and decreased. but it's really just a physical space-time that's expanding and contracting. But we call that gravity waves because we can see that it's a waveform. It's sinusoidal. It has peaks and valleys, and it has a frequency.
So it's not related directly to what I consider gravity. What keeps me on the surface of the earth is
No,
gravity.
no.
It pulls me to
The-
So these are not the waves that are keeping me on the earth.
No,
It's a
no.
different kind.
One one of the things that particle scientists will confess that they have never ever detected is something called a graviton. A graviton is a conceptual wave or particle that is the source for gravity. You can think of it if a photon is the boson to carry energy, a graviton would be the boson to carry gravity. But we don't have any technology for detecting them. We know that gravity exists, and we know that gravity is a variable based upon the density of matter that's beneath you. So if you're on the moon, the gravity's 1/6, so you weigh 1/6, but your mass didn't change. The gravitational effect on your body changed. You come back to Earth, you still weigh what you did. You didn't lose weight because you went to the moon. Yes, gravity is something that's being labeled incorrectly when we say gravity wave. What we're really saying is a wave that is a stretching and compressing of the fabric of space-time.
And we don't have anything that's measuring space-time in a wave right now.
No, we do. What we
Other
don't
than the-
have, what we don't have is the ability to artificially create that expansion and contraction. So we can't send gravity waves, but we can detect gravity waves of certain frequencies and certain amplitudes. So if a gravity wave is smaller than the diameter of the Earth, you remember you talking about radio waves that can be as big as buildings and such? Well, radio waves can actually be the size of planets. Same thing for gravity wave. Gravity waves can have a very, very low frequency, very, very long wavelength. And the wavelength of a gravity wave, it's possible for the gravity wave's wavelength to be longer than the Earth, for the gravity wave to be so long that it's measured in light years. And the recent reports involving gravity wave detections with the nanograv pulsar network is they're actually measuring the timing of regular pulsars. And if they measure pulsars in all sorts of directions, if they notice that the pulsar timing is off by picoseconds, which is, thousandth of a thousandth of a nanosecond, a thousandth of a nanosecond, you're actually saying the light, the energy coming from that pulsar took more time or less time to get to Earth. Therefore, the fabric of space between the pulsar and the planet Earth had to have expanded and contracted. So pulsar timing arrays measuring gravity, where the gravity wavelength is measured in light years. Space be big, wavelengths can get long. And when they get longer than the Earth itself, we don't really have anything we can directly measure it with, because the photoelectric effect doesn't work in that regard. What we do is we measure it indirectly. We'll go measure the timing of pulsars, which are our clock, and then when the clock changes the time between pulses by a very, very small amount, something had to make that happen. So gravity, but not gravity. The fabric of space-time expanded and contracted, but gravity itself didn't. The density of space-time didn't change appreciably, but we call those gravity waves.
Well, that wasn't nice of them. They could have tried to find another name.
Well, when you first transitioned from cassette tapes to CDs, you know what CD stands for? Compact disc.
Mhm.
Where in there does it say anything about audio? Nowhere. It's just referring to the fact that it's a disc and it's small size. So when they went to putting
That made
videos
sense,
on-
though.
when they went to putting videos on there, did they call them Video discs? Not initially. Initially, they were just digital versatile discs, or DVDs. And the diameter was the same, because that meant we get to reuse all the manufacturing machines and processes to stamp out DVDs where we used to be doing CDs.
Yes.
But you know what? There was actually a means for putting low resolution, low frame rate video on CDs. So it was appropriately named as compact disc, and it didn't get into what you could do with it. But you could store data on it, you could store audio on it, you could store certain kinds of video on it.
But it was good that they didn't name it the same thing as a disc. They went and they made it CD. You know, it wasn't
Right,
just to say
right.
that it was just plain, where it's confusing in science and other places. I mean, when you use a terminology that's every day
Mhm.
used for something else, and then you think that it's related to that item, which it's not related to that item.
Well, that's what I was getting to, is when they improved the CD and they called it the digital versatile disc, or DVD. Does that mean a CD didn't hold digital data? No, of course it held digital data. Does that mean it couldn't hold different kinds of data? No, it's very versatile. Why did you call the next thing out DVD? It was a catchy acronym. So what did you call the next one? HD DVD, high definition DVD. But that one didn't sell. That was like the Betamax of its generation. That one fell through. What did they actually call it? Blu-ray. Completely generic as to what it actually means. But it was a trademark, blue-ray. And the weird thing was, the laser that they used was not actually blue. It was ultraviolet. It only became royal blue later on when they improved. Instead of using a laser, they used LEDs because they changed the chemistry of them. And so you got Blu-ray discs. They were the next step out from digital versatile discs. They were the next step out from CDs. So sometimes business gets in the way of the most accurate naming, and sometimes it's just that's what caught on at the time.
Yeah.
Yeah.
But it can be misleading.
Oh, absolutely, it can be misleading. We don't know what dark energy and dark matter are. They may not be energy and they may not be matter, but they're just dark. We have no means of directly detecting them. As the saying goes, science is fun. So anybody have anything to say before I stop recording? Okay.